This is the second video for our asynchronous session for this week. Okay, we are going to look into detail regarding energy balance. Okay, so when we talk about energy balance, it concerns about energy changes and also energy flow in a chemical process. Okay, so what is the conservation of energy? We need to relate it with the first law of thermodynamics, where it mentioned energy neither created nor destroyed. Okay, so it will lead to this formula where accumulation of energy in a system equals energy input minus energy output. Relate with our diet. Okay, like we have discussed in the previous video. So if you eat more, activity less, so it will result in gain in weight. Then if you eat less, okay, eat less, activity more, so low loss in weight. Okay, this is the basic concept. Okay, said that this does not mean that when we talk about energy balance we always refer to our diet. So it can goes to the industrial process, manufacturing process, any chemical process. Okay, so we need to relate it with mass and also energy balance actually. For instance, if we have the input stream consists of kinetic, potential, and also internal energy, whereby potential is energy stored in any object, kinetic, motion related to any motion, internal, total energy contained by a system. Okay, so when we talk about energy balance, we cannot run away from these three terms. Okay, we have a clear picture on this. So we just now we have energy input, sorry, energy input. Also, for sure we will have energy output, but bear in mind that we have work and also heat that is goes uh, into the system or out from the system. The same goes to the heat. Okay, into the system or out from the system. So we can mention it as work done on the system or work done by the system or heat. Okay, let me write it. Work done, work on the system. So on the system, okay, on the system, work done, work by the system. Okay, different direction by the system. Then we have heat, heat being released, heat release from the system, release, okay, here release, then heat gained by the system or give to the system, or applied to the system, applied to the system. Okay, applied to the system. Okay. Okay, now let's check our understanding regarding what we have learned previously. Okay, what forms of energy possess? Just now we have mentioned something regarding energy possess. In what form may energy be transferred to and from a closed system? So we have learned about this as well. So when we talk about energy possess, we need to relate with what? Yeah, kinetic, potential, and internal energy. So these are the three energies that need to be considered. Three energies, which is kinetic, okay, EK, EP, and also internal energy. But the symbol is U. Normally, we use U as the symbol for internal energy. And then, in what form may energy be transferred to and from a closed system? It is heat and work. Now, why is it meaningless to speak of the heat possessed by a system? Heat possessed by a system. We know that heat is being transferred to or from the system, right? That's why it is meaningless to mention about heat being possessed by a system. The same goes to work. Okay, work as well. It is meaningless to mention about work possessed by a system. Okay, so the answer will be heat is only defined in terms of energy being transferred. Last but not least, we have this problem. So we need to express in terms of EI, EF, Q, and W. What is EI, EF, Q, and W? Let's look into it. Okay, suppose the initial energy of system we have internal kinetic and also potential. Okay, which is defined by EI. The final energy is EF, and amount of energy Q is transferred. Q is heat energy is being transferred from the environment to the system as heat, where if transferred from the environment to the system, we call it as positive Q. Okay, to the system gain heat, and amount of W is transferred from the environment to the system as well, to the system. So it will become positive W. Okay, okay, just now to the system, both are to the system, so it will become positive. According to the first law of thermodynamics, how must EI, EF, Q, and W be related? Since we have EI here, normally we have EI input equals to output, right? Or final energy, right? Now we need to insert Q and also W, whether we need to put it on the left hand side or right hand side. Okay, if you look at the statement, energy and also work is being transferred to the system, means we need to put it here, positive Q and also positive W, because to the system. Okay, this is the initial energy. The initial energy gain more energy through Q and also W. That's why we put it here. Or also we can rearrange this formula. It will become EF minus Q minus W. Okay, so if you look at the final answer is oh, we can see it. Sorry, I need to erase this. Okay, okay. So what will be the answer? EI system plus Q plus W equals EF surrounding, or we rearrange the formula and it will become E equals EF minus Q minus W. Now we are going to learn about kinetic and also potential energy. This is common to all of us because we have learned it since our secondary school. So this is the formula for kinetic energy, but what we haven't learned is if the flow rate or mass flow rate is being given to us, so we can express it in terms of kinetic energy as well, but the unit will be joule per second. For this one, it will be joule. Okay, the unit of energy is joule. Here, if we are given with mass flow rate, the unit will become joule per second, because here the difference is here, where we have kg here we have kg per second. And then how do we get this formula? Okay, previously we have learned that F it E equals to F equals F dot S is displacement, right? So the unit is in meter. This the unit is in what? F equals MA. So M is kg, A is acceleration, M as -2. That's why we have kg ms -2 times with m, so we will get kg m squared as -2, or in other words kg m squared over s. So we also know that this is the unit of energy is in joule, so we can relate this to. term here. Okay, then if we have mass flow rate, we will get joule per second. Okay, this is the example of kinetic energy problem that is related to kinetic energy. Okay, water flows into a process unit through a 2 cm ID pipe. Okay, at a rate of 2 meter cube per hour. We need to calculate EK. Okay, in joule per second. So how to do it? First of all, we need to look at what do we have and also what do we need to find. Okay, first of all, let's write the formula for EK, which is half mu squared, right? So we need to have U, but in the question we don't have U. And also we need to find M. In question there is no M, so we need to find these two values. Okay, first we have A. We can find A because we have the diameter of the pipe. So like for instance we have this as our pipe. So this is the diameter 2 cm ID. So we know that if D equals 2 cm, so R will be, or radius will become 1 cm. And then we also know that pipe is in a cylinder shape, so we need to use the cross-sectional area, okay, to find so that we can relate with the information given here, which is the flow rate of the water. Okay, so uh, we have A, the unit is m squared, Q m cube per second, and also we have what else? U. We need to find U, right? M per second. So how to relate these three? So we know that if we do like this, Q meter cube per second equals a U dot A, because U is M per second, A is M squared. So we can get M cube per second. It will give the same unit with Q. So we need to rearrange this because we need to find U. So U equals Q over A. So we have Q already. We can find A, right? So from here, if we find A, we know the formula is pi r squared or pi 2 squared. Okay, but this is in terms of cm. We need to change the unit later on. Okay, so we have, if we go to this part, we know that 2 meter cube per hour, we need to convert this in terms of second. So that's why we need to time with 1 hour per 3600 second. Okay, and then this is the area in term of cm. Okay, so we need to sorry, this is the area in term of cm. Okay, here 1 cm just now, so we need to convert it. So we know that 100 cm is equal to 1 meter, because this is squared, cm squared, so we need to square both values and also the unit here. So we can cancel the unit, cm squared, and then we can cancel hour with hour, and then meter cube with meter squared. So then we times all values. Okay, here we will get 1.77 meter per second, meter and then per second. So this is the first value that can we get. Now we need to find the value of m. Since we need to find the value of m, so we already have q, or also we know that q is equal to v, right? Volumetric flow rate, and we have density here. So we have learned previously how to relate a density with mass flow rate and also volumetric flow rate. So we can rearrange this formula. We will get density times v dot. So this is v dot. This is density. Then we need to convert the unit, okay, because this is in term of hour. So we need to use hour, 1 hour per 360 seconds. So we can cancel this. We can also cancel this unit. So we will get 0.556 kg per